Oh, how's that? I think it may have been muted. Thank you for letting me know. All right, so quantitative variables, they might be discrete like number of children or continuous like height, weight, and age. But the important thing about these is that we can do math on them. We can add, we can subtract, we can multiply. Differences between values actually make sense, which they don't for nominal or ordinal variables. All right, thank you, Marcella. So remember, for nominal and ordinal data, the common way to summarize these are with contingency tables or frequency tables, which just provide the total number of observations with each value of the nominal variable, or each combination of them if you're summarizing two variables at once. And whatever you can represent in a contingency table, you can also represent in a box plot. There are also pie charts, which would be another way to represent these. Most statisticians don't like them. I think they maybe have their place. They can be nice for infographics, like they can provide a nice visual appeal. They're not very quantitative, which is why most statisticians don't like them. It's hard to read directly off them what the proportions are. So, you know, this looks like it's maybe about 2/3 of an eaten pie, but it's hard to tell exactly. And this gets worse when you make 3D pie charts, because that distorts the proportions even further. At least this is looking straight down at the pie. You can imagine that if you tilted it on an angle and looked at it, it's even harder to tell what the actual proportions are. 3D pie charts are everywhere too. Here is how a statistician would display this with a bar chart. So, you know, it's obviously not as interesting as showing an actual pie, but you can read pretty precisely here what the proportions are, that about 35% is eaten and 65% is not eaten. Much more quantitative. So frequencies are just the actual counts. Proportions, counts divided by the total number of records, and percentages just multiplied by 100. And again, frequency tables or bar plots are highly appropriate for nominal and categorical data. So let's move on to the visual representations. We're going to cover dot plots and scatter plots for quantitative data as sort of the most detailed representation, histograms for one variable, and box plots. So the dot plot is the most graphical information, I think, or the most detailed graphical information you can show for a single quantitative variable. And it just shows every single observation on a number line. So this is a data set that they use in the book, which was an email data set. There are 50 emails collected by the NSA, and they counted for each one of them. Nobody even batted an eye. And they counted the number of characters and the number of lines in each email in order to try to determine whether it was some sort of a plot. And so this is a plot just of the number of characters in thousands, and it's showing the mean here, which is about 12,000 characters. The scatter plot is a two-dimensional equivalent of the dot plot. So you look at two variables at the same time. And here it's showing not just the number of characters, but also the number of lines in the email. So along the x-axis, if you were to project all of these down onto the x-axis, that would be your dot plot. But we're also showing with the y-axis here the number of lines in the email. So you can see the relationship between these two variables and see that generally it's a linear relationship between them. Here are a few things you can read off of a scatter plot. You can assess that whether that relationship is more or less linear, like can you draw a straight line that represents the relationship from the left-hand side to the right-hand side. You can kind of read where the point's most dense. You can see that, you know, most of the emails, it looks like, are down in this range. They're shorter emails and there are smaller numbers of really long emails. I suppose this is not counting all of the text that gets included in replies, or else they'd probably all be long. You can assess heteroskedasticity, which if you look this word up and there's a stats wiki, it starts out by saying heteroskedasticity is a hard word to pronounce, but not a hard word to understand. This is just a preview. Heteroskedasticity becomes important later in the course when we learn about t-tests. But all it is it means that the variability of your data is the same throughout the range. So if you look at this, you see that there's like not much variability here and quite a bit more up here. So you would say that this is heteroskedastic. It's not homoskedastic, which would mean that there is no variability in this, or that this variability is the same throughout the range. So that's just a preview. Don't worry about it, but I figure the more times I mention it, the more likely you are to remember and be able to say heteroskedasticity. And you can also check for outliers. And outliers, it can be hard to formally define what is an outlier. There are a number of definitions that people use, but they can take, it is kind of fundamentally a qualitative thing, whether something is an outlier or not. It means, is it like all of the other points or not? And when I look at this plot, I don't really see any outliers. They all kind of look like they're following the same trend. I don't see one down here, which would be an outlier. I don't see one, you know, way up here, which would be something with only a few characters, but a lot of lines, like someone just typing one word per line or something like that. No super weird emails in this data set. So that the scatter plots and the dot plots, they show every single data point. But they're actually not always the most informative. And when you just want to look at a single variable, I think you'll rarely see someone do it as a dot plot. Much more commonly see people show a histogram. And what the histogram is you take and artificially create categories. And each category is a range of possible values, and you count the number of your records that fall within each of those ranges or categories. And then you plot it like a bar plot. So this is a bit of review. Again, I know, but so in this case, these are weights. There are 3 categories between every 50 units here. And this is just the frequency, the count. So that's 3 records have between 100 and about 117 here. And histograms can be very useful for observing things like skew and outliers. I have some examples of that. But yes, question.
So is a bar chart or a bar plot, each bar is just one value, whereas in histogram it's a range?
So the question, what's the distinction between the categories in a bar chart and in a histogram? The distinction, I think, is that in a bar chart, you're representing a categorical variable. So it's just one value of the categorical variable is being represented by that bar. Whereas with the histogram, you're binning together values of a quantitative variable. So yes, there can be a number of different quantitative values that all get put into that category. But in that process of binning the quantitative data, you're creating a categorical variable. So it is totally equivalent to a bar chart for an ordinal variable, because the order here does matter.
So the variable, a categorical variable in a bar chart could be a quantitative value, right?
Yeah, so the categorical, the categories in a bar chart could be a number. I mean, it could be a number of children, something like that. The important thing is that anytime you're making a bar chart or a histogram, you don't want to be fully representing a quantitative variable. You don't want to have a line for every single data point, because for quantitative data, every single value can be different. So that's a useless histogram. You would just have, a 1 for every frequency. It wouldn't be informative. So you have to, you have to create the possibility of having more than one record fall in one of these ranges in this discretization or this binning process. But how you do that, how wide or how fine you make these bins is an open question. There isn't a right answer. And you can do it a number of different ways. So on the left, here is what you could get by making those bins narrower so that there are fewer records in each one. So there are a couple with just 1, some with 2, and at most 4. In the middle here, so that was with 10-pound bins. With 20-pound bins, you get on average twice as many per bar. So we have up to 6 here, and making them even wider, you're doing more summarization, you're putting more things into the same bin. And how you do that is depends on how much detail you want to show. And your software, your SPSS or whatever, will have some kind of algorithm that it uses to try to make an automatic decision. But it is something that you can change if you don't like the decision it made. I mean, if you see there are only 3 bars and you have 100 data points, you might want to separate them more. That algorithm is a little bit tricky, that how it automatically does it. Like if you have a few data points, it's going to make fewer and larger bins. If you have more data points, more records, it's going to try to make more fine distinctions. Just so you're aware that when you click on the button to get the bar chart, that there's some automatic decision being made there about how to categorize your quantitative data into discrete bins. Question?
Just to make sure that I understood your definition of the general difference between histogram and bar plot. A data point for a histogram can fall away from an actual point, like on your definition because it's a range. Whereas in a bar plot, it can't do that because it's a category.
Yes, so the question is, again, about the distinction between a bar plot and a histogram. And
because on a data point, like for instance, just your example of number of children, you can't have 1.5, right? When you're using it to calculate data, you're not going to have averages in there. But in something like this, you can be, you know, I can't really read it. You can be 110, so you can be in between.
Yeah, the real distinction is that in a histogram, you're doing a certain amount of summarizing of the data. So, and a histogram is something you do for a quantitative variable. A bar plot is something you do for a categorical type of data. So another question? Yep.
I wanted to ask you about the definition, in this case, the bin size too.
Yeah.
Saying bins, I may think of bins something else with respect to the graphical, just to better visualize.
Yeah, so what do I mean by bins? I'm thinking of bins as being, each of these bars is a bin, and then you can imagine your quantitative data, you drop them in whichever bin in which they fit and watch the level in that bin rise. So each one of these is a bin, and they're all the same width in one of the histograms. All right. So the things that we look for in a histogram, a big one is the shape of them. Part of that is skew, which has to do with the symmetry of it. If you look, and it kind of looks like what you see to the left of the center of the graph is the same as what you see to the right, then you would say it's symmetric. If you see a long tail going to the left, it's a left skew or left-tailed distribution. And likewise, if you see a long tail going to the right, that would be right-skewed or right-tailed. And this is a basic important thing to know about a quantitative variable, and one of the big reasons that we plot a histogram. Can anyone think of an example of, in real life, what might be a skewed distribution? Something that's left skewed or right skewed? Yeah?
Maybe, like if you were to look at death rates of cancer, that specifically affects older generation, you know, mortality.
Yeah, mortality rates. So say you're looking at
looking at age and then mortality of prostate cancer, you're going to see like another.
So you're looking at people who have had prostate cancer and people who died of prostate cancer and the age at which they died. You think that would be right skewed or left skewed? Yes, left skewed, because you're going to have quite a few people, probably in their 60s, 70s, who die of prostate cancer, and then you're going to have just a few maybe in their 20s, or maybe in a very rare teenager who dies of prostate cancer. So yes, that's a good example of something you expect to be left skewed. Is there another? Yep.
I was just thinking something simple like income, like percentage of people that have a higher income would be something that would probably skew to the right.
Income is a great example of a skewed distribution and something that skews to the right. You have lots of people with incomes right around the typical amount, and there's only so low you can go beneath that, so it's hard to be skewed too much below, but you have the, you know, the presidents of big companies at the right, so it goes almost unlimited to the right, so that is a right skewed distribution. And I see online someone said housing costs. It's another good example of a right skewed distribution. You have a few places that cost, I don't know, $50,000 a month, but most of them in New York, you know, are around, I don't know, $1,500, $2,000 a month. This is something you can determine from a histogram. So in our data set, here's the number of characters in an email. As it points out, the distribution is strongly skewed to the right. So you have lots of emails that have, you know, between 0 and 5,000 characters, but then a few, there's one that has over 60,000 characters. Someone wrote a book in their email or something like that. So shape. Another aspect of shape is the modality, which is sort of the type of mound that you see. Occasionally, your shape will be uniform. That would be like a uniform distribution. A lot of times, it will be something like this, which is there's just a single mound in the data. This is maybe a little bit of skew, but not especially. This is more or less, and we'll be talking about the normal distribution lots in this class, but this is kind of more or less normally distributed. And it's definitely unimodal. You know, it doesn't mean it's perfectly, there's only one hill. You might think of this as an extra little mound, but that's not really enough data to call something bimodal. This, on the other hand, we have two distinct modes with a fairly large island between them there. This is what we would call a distinctly bimodal distribution. And this is, since there's this one bin here with very, very few counts, this might be a multimodal distribution, which is pretty rare to come across. And then finally, you can easily spot outliers in a histogram. Just, you know, something, there's like this long desert here with no records, and then this one single observation up there, which looks like an outlier. And in general, when you see an outlier, it deserves some attention. You want to take a look at that record in more detail, see if you can understand why it's an outlier. And it may or may not be justifiable to remove it. If you can determine for sure that you understand why it's an outlier and it's not for a reason that's relevant to your research question, then you want to remove it. But it might actually be a part of your population distribution, and you might be skewing your analysis by removing outliers because they're actually a part of the population. So summary, to interpret histograms, the big things that we're going to look at are the center, where the main part of the distribution is, where most of the data points lie, and the spread and the shape. So the spread, by this all I mean is you know, how much variability is there in that variable. And the shape has to do with symmetry and modality. Hi, Tony. Finally, the box plot, which I think is an underutilized, very nice way to represent quantitative data. And it lies sort of somewhere in between the histogram and the dot plot for the amount of information it shows. It does more summarization than a dot plot, and actually maybe it does a little more summarization even than the histogram, but it is also more quantitative than a histogram in that it has several numerical summaries, which we're going to cover in a moment, that it represents. So here, if this is a normally distributed quantitative variable. So it's centered at about 50. Its range, it goes up to 90, down to about 10. And this is, I'm drawing what's called a density plot here, which is just like a very fine histogram just to represent the population here. The box plot, it puts a line here right at the center, at the median of the distribution. So that's where there are equal numbers of observations above and below it. And then it encloses this box at the first and the third quartiles. So quartiles are where quarters of the data lie. So the first quartile means that 25% or a quarter of the observations of severity of something, in this case of pain, fall below that. And the third quartile is where 75% of the observations fall below it, and 25% would fall above it. So this difference between the first quartile and the third quartile, we call that the interquartile range. And it's a measure of spread of the data. And then you have these whiskers, they get called whiskers, that extend out beyond by a specified amount. And it goes out either to the furthest data point, the most extreme data point, or to the median plus 1.5 times the interquartile range, whichever is smaller. So it will go out beyond the most extreme data point if it's within this median plus 1.5 times the IQR. So you can kind of see it here. This is the IQR. It's about 20 wide or something. So 1.5 times that would be 30. So it's about 3 of 1, 2, 3. So that's a box plot. They're very popular with statisticians because they allow you to stack up one distribution next to another and compare these important quantitative measures, numerical summaries of the data. Like this. So if you have height, a quantitative variable, you have males and females, and you have a sample with both of them, you can directly compare them to each other and see where the center of the distribution is, the spread, and where the outliers are. Whereas it would be more difficult to do this with histograms, for example. Any questions about the box plots? You'll learn how to make them in SPSS, and you'll use them in this class. So just to wrap up these visual representations of quantitative variables, starting from the most detail was the dot plot and the scatter plot, and then the histogram is doing a certain amount of summarization, and box plot doing more summarization but also being more quantitative. Okay, so numerical summaries, and I've given some a little bit of advanced discussion about these already. The mean. This is the one, remember there were examples of people calculating the mean back to like 400 BC or so. And the reason is because it's a very useful and intuitive measure of where the center of a distribution is. So you go and collect a sample of 40 observations. How are you want to have some understanding of, what's the most typical value. One way to do that is with the mean. So this is called capital sigma or summation notation. This is the Greek capital letter sigma, and all it means is a sum. So if x is a quantitative variable, each individual observation is, we're using a subscript I here, where I between 1 and the number of records represents each individual. So x1 might be the first record that we gathered, x2 would be the second one, etc. up to, if n was 100, then this would be a sum of 100 different values. You just add them all up, divide by the total number. Now the median, you don't do any adding at all. All you do is sort your observations from smallest to largest. And if it's odd, it's just the middle observation. And if it's even, it's the average of the two middle ones. That's one way of defining the median with an odd number. It's worth noting, and just kind of keep this in the back of your head, that different software calculates the median differently. So especially for small numbers of observations. If you have only 5 observations, you calculate the median in Excel and you calculate the median in SPSS, you're going to get different answers. C'est la vie. It doesn't really matter which one you do, but there are like 7 different formulas for calculating median. If you do it by hand, this is the way you're going to do it, because it's easy to do it. And it's also the 50th percentile. Yes?
Depending on the software,
Sorry?
depending on the software you use,
Uh-huh.
what's the difference between the two?
It can be big. The question is, how big is the difference between the medians? I don't think it's big enough to actually matter. Where it's big is if you have like 4 observations. It can be quite different, but honestly, your median is not that well defined when you have 4 observations. So it doesn't really matter. If you have 100 observations, you will not notice a difference at all. So it's for those small cases where that difference in the different calculations becomes larger. Yes?
What is the difference in terms of reliability between the median and the mean? What would you use for certain kinds of data?
Right.
versus others?
So when would you use the median and when would you use the mean? Median is really good for, and we'll get into this a little bit more, but median is a robust statistic. So if you have outliers, you have a skewed distribution, median is good. Mean is really good for normal distributions, more or less. I guess I could add though that you can always use median. Like if you have a symmetric distribution, the mean and the median will be almost the same. I guess the reason that mean is nice for a lot of statistical tests. So, but yeah, it is really for normal-ish distributions. Any more questions? All right. So, as an example, you've got the 7 dwarves. The median height is just the height of the middle dwarf, the one sitting in the middle when they're arranged. So that's the thing to keep in mind about the median. One is that it's an actual value. I guess unless you have an even number, it can be the average of 2 values. But the other thing to note is that if you replace the dwarf on the right with the tallest man in the world, then the median doesn't change at all. So it's robust to outliers. It doesn't matter whether your largest observation is close to the second largest or completely off the charts. It doesn't change the median. The mode is the value that occurs most often. So this is well defined for, for categorical ordinal variables. For numeric values, it's less, or for quantitative variables, it's less well defined because you have to do some amount of binning or discretization, as in the histogram, in order for the mode to be defined. So, but for a specific size of these bins, then the mode is just the highest bin. We don't really use mode a whole lot because it's not that well defined for quantitative variables, but it's good to know what it is. Of course, if you have two different bars that are the highest, then the mode isn't even defined. It's a bimodal distribution. It has two modes. There's the mode. When you have skewness, it will, so when there's no skewness, these three measures will all be very close to the same, but the more skew you have, the more different they become. And you can detect skewness without even looking at a histogram or a box plot, just by looking at the mean and the median especially. So if you have a long tail to the right, those high values are gonna pull your mean to the right, and your mean will be larger than the median or the mode. So in the case of housing costs or salaries, the mean is gonna be higher than the median. And that's worth keeping in mind, just because you will often hear people talk about the average, and it's not always totally clear what kind of average they meant. Like, it should, usually average should mean the mean, but there are other measures of that central tendency, like the median. So when you're talking about something that has extreme right skew, your mean might actually not be a representative value, like talking about mean income in a group where there's one person who's earning $1 billion and then a bunch of people with normal incomes. The mean is not going to be representative of anyone in that group. And then if you have a left skew, again, it just draws the mean to the left. So percentiles are a really nice summary of the data that it is just a measure of what % of your observations are less than a particular given value. So in the case of the number of lines of an email, the percentage is a number of lines. So it's in the same units as the thing that you're observing, and it's the number of observations or the % of observations that are at or below that value. And the quartiles, again, split the data into 4 parts. The first quartile gives you the smallest quarter of the data. The second quartile, between Q1 and Q2, is the quarter that's just below the median. The third quartile is the quarter that's just above the median, and the top quartile is the observations that are greater than 75% of the data. Now, the range is just the difference between the largest and the smallest value. What do you think So out of these measures of spread, we've talked about range. Oh, we have one more. I'll ask you this in a moment. Variance and standard deviation. Then I'll ask you this. This is kind of the major measure of spread that we'll use. And to calculate it, it's more complicated than the others. For the range, it was just the difference between the largest and the smallest value. For standard deviation, you need to calculate the mean, then you need to take the difference from each value from that mean, and then take the average of the square of those differences. So there's a few steps involved in it. And then finally, the square root of it. By the way, this n-1 on the denominator has to do with something called degrees of freedom, which we'll talk about more in the course, later in the course. But just to give you an idea of, so it's not quite an average of the squared differences from the mean, because if it were just an average, you divide by n. But it turns out that if you divide by n, you actually underestimate the standard deviation. And I can give you a kind of hand-waving explanation of why that is. You can imagine that when you take, suppose your sample just has 2 observations in it. Where is the mean of those 2 observations? So let's say the observations are 6 and 10. What's the mean? 8. It's right in the middle of those 2. Now, that estimate of 8, keep in mind that is an estimate from our sample. That's not the actual correct value for the population. And we have placed that mean in the place that minimizes the standard deviation. If we were to use the actual population value, which maybe is 7 or maybe 9, the standard deviation would be larger. So it's because you're estimating the mean from the sample in the place that gives you the smallest possible standard deviation. That's why you underestimate the standard deviation if you divide by n here. But if you divide by this degrees of freedom, then it turns out it's not biased. Any questions? This is just a little graphical representation of what it looks like for a few different distributions. And you don't need to know what normal, log normal, exponential, and uniform distributions are. You should know what the normal distribution we'll talk about a lot more. The uniform distribution is kind of an intuitive one. It just means that all possible values within the range are equally likely. So what I plotted here was 40 observations from a normal distribution with mean 0 and standard deviation 1. And you can see how some of them, they're close to the mean, and a few of them, most of them are close to the mean, and a few of them are a ways away. And these red lines are showing the these x minus x bar, these differences from the mean. For these distributions, just suffice to say these happen to be skewed distributions because you have really a lot with very little deviation and then a few with a large deviation. Oops. And then when you square them, you see that those differences actually become much larger. So the first thing you notice is that then they're all positive because it's squared. Before there were some that went up and some that went down. Now they all go up, the squared deviations. And in the data sets that had some skew in them and some outliers, those outliers become even more extreme. So that's the important thing to know about the standard deviation, is because it's the square of these deviations, it's really quite sensitive to outliers, because the difference from the mean gets squared and it exaggerates it. So the things to know about the standard deviation, one is that it has the same units. So if the variable is height in inches, then the standard deviation is also in inches. And it's a measure of the spread of the data. It's just one measure of spread. There are several, but it's a useful one in a lot of cases where we have a more or less normally distributed variable. It's 0 only when every observation is identical. Otherwise, it's always positive. It's never negative, because we're taking squares and squares are always positive. And the more spread, such as due to skew or due to outliers, the larger the standard deviation becomes. Or just due to there being more of a distribution of the data. And again, it's not resistant, so an outlier can have a large effect on the standard deviation. So it's a summary of the data. It doesn't tell you everything about it. And as a summary, it's not giving you complete information. So there can be different types of distributions that all give you the same standard deviation. And here's an example from the book of 3 different quantitative variables that all have a mean of 0 and a standard deviation of 1. So just keep that in mind. Anytime you're summarizing the data, you're not getting the complete picture, which is why you know, a numeric summaries can tell you a fair bit, but not everything, and it can be useful to look at graphs as well to get a better understanding of your data. This is a complete enough listing of measures of spread that you might come across. The interquartile range, which I mentioned, is just that difference between the 75th percentile and the 25th percentile, or the third quartile and the first quartile. Median absolute deviation is meant to be a sort of robust equivalent of standard deviation. So instead of squares of differences from the mean, it's just the differences of each value from the median. And actually, it's absolute. This should be an absolute value, and it's the median of those differences. And then range is just your maximum minus your minimum values. And I put stars by these 2 because they are robust measures. They're robust both to outliers and to skew. Yes?
Usually the second one, the median absolute deviation, requires that formula, median x minus b.
Yeah, so if x are all of your observations, I wonder if I can get, so this, we should probably put a subscript here. And really, there would be a summation here too. This has to be summed from I equals 1 to n, and this is an absolute value. So I'll put bars here. So it's just, you take, if there's a negative sign, you take away the negative sign. So for each observation, it's just how far away it is from the median, and you add those up and take the median. I believe this should also be divided by n, because it's an average. We're not going to use MAD in this course, but I just want you to be aware of it as a robust alternative to standard deviation. This example here, this was a very skewed distribution. And I just show here, this is the median because it's the middle of a box plot. And this is the mean, just showing how the mean is shifted up from the median by this skew. Yes?
Can you explain what you mean by robust?
Yeah, what do I mean by robust? By robust, I mean that it is not sensitive to outliers or skew. It means that it's hard to change it. So you can't make it change just by adding a couple weird values. So robust, I mean, is kind of an opposite to sensitive. And we have a slide on robust statistics. So here are the number of characters in these 50 emails, courtesy of the NSA. In the original data set, there was one that had about 60,000 characters in it. And just to show what here is meant by robust, it compares this data set to what if we dropped that one largest value, and then what if we replace it with an even larger value? So our robust statistics here, let's look at the measures of central tendency first, the median. When you drop it, it goes from 6,890 down to 6,700. So it changes by about 100. Whereas the mean, well, it also changes by a little over 100. So the mean is a little harder, it's not super sensitive compared to the standard deviation, which I'll point out in a second. But when we make this a more extreme outlier, you see that the median doesn't change at all, and the mean does change a fair bit now. Measures of spread in general are more sensitive to outliers than the measures of central tendency. That makes sense, right? Because it's a measure of spread, and the more extreme your outliers, there is sort of more spread in your data. But you really see that here with this outlier. So the standard deviation, when we got rid of it, went down by about 2,500, and then when we took it up here, it went up by almost 3,000 or almost 10,000. So the standard deviation, more so than the mean, is quite sensitive to outliers, and this interquartile range is relatively robust to that outlier. Here's a summary. We're pretty well out of time, so I think I'll just ask if there are any questions about what we covered. I put the summary here just to try and, so you'll have it's a one-page note of what was important from this lecture, so you can just look at it and know that's what we covered and what you want to make sure that you're comfortable with before the exam, and also what's important for you going forward in your careers and in the rest of this course. All right. Oh, a question, yes.
Yeah, so the mean, I think it's pretty obvious how you calculate it, but would we be expected to reproduce the capital sigma notation?
No, I'm not going to expect you to reproduce any formulas. But anyways, your exams are open book, so I don't expect you to memorize things. What I expect is just for you to be comfortable with these things so that, you know, you can do some calculations in them in a reasonable amount of time. And so when I ask questions that are more of an intuitive nature, and, you know, I'll try to come up with just some sort of qualitative, like seeing if you know, understand some of the discussion about like what is a robust statistic, things like that, that you have a good understanding of them. But yeah, no, I hated memorizing stuff as a student, so I don't make you do it. And it's not, this is not a formula centered course, so. All right, if there are no more questions. Oh, yes.
Rewind to that last slide too.
Yeah.
Basically, we're looking at that graph over there, and then saying the spread is over there. That first one is the original. That little dot, that's the outlier, right? Because it's outcast, right?
Yeah. So there's the outlier.
And then applying this, I got kind of
okay.
Example, like the original scenario.
Yeah, so the scenario here was that we just drop that point. We decide that it's an outlier and it's no good, and we drop it and see how that changes the median, the IQR, the mean, and the standard deviation. And then the final scenario is that you actually change it to be a much more extreme outlier. So you take it from 64,000 to 150,000 just to see how much that changes these estimates. And the median, it's like that Seven Dwarfs example, changing an outlier doesn't change the median. And all of the rest, it does change. And you can see how it changes the standard deviation more than anything else, followed by the mean.
Because the differences are greater, yeah, not robust part, right? You can see
right. Yeah, so it's just a lesson showing you that the robust statistics, they change less than the not robust statistics. They're robust because they're hard to change. They're stubborn. And I see we have some online questions. Will exam questions, I'm gonna go ahead and flip here and answer these. Will exam questions be similar to the application questions at the end of the chapters? I'm not sure yet. Most likely, yes. I'll take a look at these in a little more detail, and I will also give you some explicit, like, sort of warm-up practice questions for the exams. But I need to look at these applications questions a little more carefully to decide whether they're good, similar exam questions. But the exams, I don't want them to be a surprise for you. If you've attended the lectures and the labs and you've done the assignments, there will be no surprises. I take notes on my iPad. Is that okay for an open book exam? Yes, it is. You'll be allowed to bring your own iPad or your own computer. And the only thing you won't be allowed to do is to use the internet during the exam. You have to be self-contained. You can use the course textbook. You can use any notes. You can use anything that I've posted on Blackboard, but just not the wide world of the internet. Any other questions?
Will it be in this room?
Where will the exam be? It will be down in the computer labs. Yeah. So you can use your own computer, or you can use the computers that are there. All right. So I'll see you all downstairs in the lab in 5 or 10 minutes.